Hi, Mick McQuaid here with iste782 Visual Analytics, and now we're talking about the first chapter of part 4 of our textbook, R for Data Science. This chapter is on model basics. And we're going to neatly sidestep the question of defining models by instead talking about the goals of defining models and the plans for defining models. So our goal is going to be to provide a simple low-dimensional summary of data, and our plan is to partition data into patterns and residuals. And there are a number of aspects of models that we have to familiarize ourselves with. The first is the family of models that we're talking about. So we're mostly going to be talking about linear models here. So the family of models can be described as y equals beta naught plus beta 1x, or in the terminology used in this textbook, y equals a1 plus a2x. Then within that family of models, our goal is to find a fitted model. For example, y equals 7 plus 3x. So this fitted model has these coefficients that represent the best that we could find from the family according to some criteria, such as least squares or whatever criteria it is that we're using. And this model, even though we say it's the best from this family according to this criteria, it may still not be any good. That is to say, it may not be useful. So a good example of that would be a model that represents a cloud of points that lie in more or less a circle. Any line through that will be as good as any other line, or in other words, as bad as any other line. It's not useful. And no matter how good the model is, it certainly doesn't represent the truth completely. So no model does. If you've studied modeling at all, you know that. Even if you haven't, you might have encountered, here let me just point out this famous Borges short story called On Exactitude in Science, in which he describes a map that is the same size as the territory. And this Wikipedia article about it also mentions a Lewis Carroll story, which has the same situation, that there is a map that has a scale of 1 to 1. Umberto Eco also expanded on this theme in the short story on the impossibility of drawing a map of the empire on a scale of 1 to 1. So there are plenty of domains in which people talk about the fact that a model is not the complete truth. Okay, so our prerequisites for this are the tidyverse library and the model R library. And then even though we're not going to encounter any missing values and stuff we're going to go over, our authors recommend that we employ this option na.action equals na.warn, which prevents missing values from being passed over silently. Okay, now there are 5 data sets in this, or about 5 data sets in this chapter, simulated data sets, just to illustrate the points about model creation. And so this is the first one. Sim1 is the name of the data set, and we plot it using ggplot and the geom point, which gives us a scatter plot. And we can see in the scatter plot a pretty good idea of what the model should look like. But we're going to abandon that intuition and go through a very crude method for creating a model. So we're going to start out by randomly generating models, as if we don't have any intuition. And these models, there are going to be 250 models. And what we're generating, so you recall the equation y equals a1 plus a2 times x. So a1 is the intercept of a line, and we're going to generate 250 intercepts in the range of -20 to 40, and they're going to be generated randomly from a uniform distribution. And the same thing is true of the slopes, except that they're going to be generated from values of -5 to 5. There will be 250 of them randomly generated from a uniform distribution. Now you might wonder, so R has quite a number of random number generators built into it. There are like 17 of them or so altogether. So if you type ! distributions into the R console, you'll get help on distributions that includes a list of all the distributions for which there are random number generators. So basically we're creating a table that's 2 columns here, one column for the intercept and one column for the slope. And we can overlay these models on the data. So the data is still sim1, and we're still going to use geom point to display it. But we're also going to use geom AB line, and the intercept is going to be A1, and the slope is going to be A2, and the source of the data is going to be models. So that's the models that we created in the previous step, that table that we created in the previous step. So they're going to be 250 lines, so it's going to be quite a mess. And in order to make it possible to see the lines, we're going to reduce their opacity. So alpha equals 1/4 means that their opacity is only going to be 1/4 of full opacity. So there's what we get. And none of these models are particularly good, and they're just random models. This isn't really what we want, but if we had no intuition, this is the best that we could do. What we want is something that would minimize these error lines. So here's a picture. This is just a picture I've copied from the textbook of a line. They've just selected a line and drawn it through, and drawn lines to all the data points. If we could minimize the sum of the lengths of these lines, that would tell us how good this line is. And we would like to find the model with the smallest such sum. So to do that, we're going to go through several steps. So there's of course a built-in function to do what we're going to do, but we're just learning the process, so we're going to do several steps here. So the first step that we're going to do is create a function that generates, given a pair of inputs. So remember, we have 250 inputs. So if we're given a pair of inputs, say 7 as the intercept and 1.5 as the slope, and given this data, it will spit out a prediction. And so we've written a function here that does this. This function, which is called model1, takes in a vector, consists of the intercept and slope and the data, and it generates a number. For each value that it's given, it generates a number that is the first component of that vector plus the x value of the whatever the data is times a2. That is the second component of the vector. So it's going in our case it's going to be 7 plus whatever the x value is 30 times, because there are 30 values in sim1, times a2. Okay, so given this one prediction and this input data, it's going to generate as many values, as many outputs as there were inputs in sim1. So that's 30 outputs. Now we're going to then take that function, so that function is right here, and wrap it up in another function called measure distance. So that function takes in the same information, the vector of the intercept and slope and the input data, and it first takes the predicted value, the actual value, and subtracts from that the output of the model. This is the predicted value of the model, and that's called the diff. and then it takes the square root of the mean of the square of diff, and it spits that number out. So this function will take in as many data points as we have the 30 data points from Sim1 and spit out one number that corresponds to how good predictor this intercept and this slope are. So, and this is a remarkably good number. This is better than what we've got in our data set. We don't have this pair of numbers in our data set, I don't think. Then we're going to wrap that function, the function on the previous slide, we're going to take that function and wrap it in a function that does this 30 times. It's going to give us basically a table of outputs that's going, and we're going to mutate the distance table so that we have A1, A2, and the output of SimDist, which is a score. So it's easier to just look at the data here. So we have the A1 value, the A2 value, and the score. So this is telling us for each pair, and we've got 250 of these because we have 250 predictions. For each one of these predictions, it's giving us a number that is the score of how good that prediction is. And here, in this group of 7 that we're looking at here, this one is by far the best. This is really good. We want this number to be as small as possible. So this, for example, is really bad. Okay, and this one is really bad. This one is really good. It's still not that good in absolute terms, but it's good in comparison with what we've got. Now we can see that by overlaying the best models that we have on the data. So we're going to ggplot sim1 again. So this is our original data, and we're going to just plot it with dots of size 2 and a color of gray 30. And then we're going to add to that some AB lines. And the AB lines are going to be, what we did this before with all 250 with the intercept of A1 and the slope of A2, but we're going to do two things differently. We're going to color them according to their score. This is the score in DIST. And the data from that we're filtering from the models is to rank the DIST and give us only the top 10. So rank 1 is the best one. That will be this one with the smallest DIST number. And so rank 2 is the second smallest, and so on to the top 10. So we're just going to look at those, and we're going to get those lines. We're going to have a scatter plot from here, and we're going to have 10 lines from here. So let's look at that, 10 colored lines. And the colors are lightest for the smallest distances. So this is the best line that we've got. It's not very good, but it's the best one that we've got from among our random models. Now there's another way that we can look at this. We can compare these models as scatter plots of A1 versus A2. And so let's do that. I'll come back to this in just a second, but let's take a look at that. So we have A1, the intercepts, and A2, the slopes, and we've highlighted the best ones. And let's see how we did that. So let's just go back and take a quick look at this. So this is the scatter plot of all of the points, all of the A1s and A2s, so there are 250 of these. And this is a scatter plot of the 10 best ones with a larger size and a red color. So imagine these as happening one at a time. The way that ggplot plots is it first lays this down and then it lays this down. So this is kind of the basis, and this is large red dots, and then we're putting small dots on top of that are colored by negative distance. So the small colored dots are kind of in step 2 of construction of this plot. And you can see that there's a very conspicuously empty area here where if we had been luckier, our randomly generated numbers would have come up with some answers in there. But what we can do, so we're going to stick for a second with the really crude method of model building. We're going to say that this is the right neighborhood to be in. We know we should be in this neighborhood. So let's only look at this area and generate some new values just in this rectangle. Okay, so this is going to be the rectangle from about 1 to 3 on A2 and -5 to 20 on A1. And so that's what we're doing. We're creating a finer grid of A1s and A2s, and we're going to subject that finer grid to this same function to see how good it is. And then we're going to just plot it. And this plot is exactly the same plot that we just did, except that it's with the new data. And it's going to look better because we've used a solid grid instead of just our random search. So in the top 10 are clustered together here. And so what we could do, if we wanted to continue this process, is then just go into this neighborhood and create a finer and finer grid in this neighborhood. And eventually we would find, after some extremely tedious exploration, we would find the best, and it would stop getting the best coordinates, and it would stop getting any better. Oops. Oh, so I kind of skipped over something here. So we need to take a look at those values. So those top 10 lines are a lot better than what we had before. A lot better. So, and we got those with the same exact plot that we did before. Okay, but they match our intuition much better. So as I said, we could keep doing this, or another thing we could do is use a well-known optimization method. And that optimization method that we're going to try next is represented by a function called optim. And optim is going to take measured distance. This, if you recall, this was the function that we developed to evaluate each individual coordinate pair. And optim is going to also take in the simulated data set, and it's going to spit out the coefficients. It's going to spit out an object which, among other things, has as coefficients the best possible pair of intercept and slope, and that's in this variable best $par. So best $par bracket 1 is the intercept, and best $par bracket 2 is the slope of the best result. So now we can plot this, and keep in mind these numbers, 4.22 and 2.05. These are actually the best numbers that we could get. Okay, so we plot that, and that is the best line that we could get according to the criteria of Newton-Raphson search. So there's a name for what optimum does. It's called Newton-Raphson search. You probably have encountered Newton's method, and so this is a refinement of it. A better method that we could use, though, better than optim, would be the method that R uses. So this is possibly familiar to you already. If we just do linear model in R, LM, the LM function, y predicted by x, data sim1, this spits out a very sophisticated object, a very sophisticated model object. And if we take the coefficients of that model object, we find that they're roughly the same as the Newton-Raphson method spat out, which are 4.22 and 2.05. But we need a more general method for visualizing the models than what we've just seen. We need it to work for both predictions and residuals. So let's construct that. The first thing we're going to do is just generate a grid over the data space. And then we're going to add predictions to the grid. So these are the predictions of our best model. These are the predictions made by this model, which we know to be the best. And when I say we know that, I mean, I'm skipping over the math, but you can, so in mathematical statistics classes, you would have to do a proof that shows that that's the best method. Or excuse me, that shows that that method yields an optimal answer. And that's not that it's the best method. It yields an optimal answer that's not subject to local minima. Okay, so now we're going to plot the predictions. So these predictions lie along a line, and we're going to use those predictions to form the line. The line is going to be colored red. By the way, Hadley Wickham is from New Zealand, so he uses these spellings, but you can just use the American spelling of color, and it will R will understand that as well. And this is the thickness of the line. So the line, so this just puts the same line that we saw, roughly the same line that we saw before. This is the absolute optimal line that we could get. Now we can add residuals, and the residuals are the differences between the predictions and reality. So this is the reality. This is the difference from the reality of what we predicted. I mean, yeah, the difference between our prediction and reality. And we can plot those. The residuals are going to be centered around 0. And we can plot those using either a histogram or, in this case, a frequency polygon. And like the histogram, you should manually set the bin width and play with the bin width. Don't just accept a default for that. You should always plot the residuals and see if there's a pattern to the residuals. If there is a pattern to the residuals, the model is not very good. If there's a pattern to the residuals, it means that the model hasn't captured some of the pattern in the data. So if you recall, our plan was to divide the model into patterns and residuals. And these residuals show no pattern at all. In other words, there's no way that I can predict the y value based on the x value. The distribution is the same all the way across here. Knowing that this value is 8 or whatever it is, or 9 or whatever it is, doesn't tell me that this value is minus 1.5 or whatever that is. So we're always looking for that. And the reverse is not true. We don't know for sure that the model is good just because there's no pattern of residuals, but we know for sure that the model is problematic if there is a pattern in the residuals. Now the modeling functions that we use are converted from formulas that we actually write out into R into functions like this. And we can see the mechanics of what R is doing by writing out a function and a data frame and getting a data frame back that shows the model equation. So let's do that. And so here's an example of a simple data frame and a simple model. And model matrix returns this matrix for this model. And sometimes you need to be able to see this. You can explicitly drop the intercept column. So let's go back to this one. It has an intercept column here. And you can drop that by saying -1. And you can add more variables. So if you recall, this data set had 2 predictors. And so we can add more variables and see that the model matrix gets bigger. Categorical variables are handled differently, and you can see that by doing model matrix also. So here we have a response variable, so think of this as y, and think of this as x. And so when we try to predict y on the basis of x, one of the x values becomes assigned to 1, and the other one is assigned to 0. So here's a simulated data set. So here's the second of our 5 simulated data sets, Sim2, and this has a response variable and a categorical predictor. So the predictor x takes on one of 4 values, and the response is continuous from minus something to 10 or so. We can fit a model and generate predictions here. So we're going to fit the model y is predicted by x here, and we get basically one prediction for each value of x. So and this prediction, it says here, is the mean for each category, and we can visualize that by plotting the points. So we'll plot all the points here, and then we'll also plot one point for the prediction grid. So this is going to be a total of 4 points. They'll all be red, and they'll be quite large, and they'll be the mean for each category. And you can see that just at a glance that the 4 red points are the means for those 4 categories. So another data set we have is SIM3. SIM3 has a categorical predictor and a continuous predictor. So the categorical predictor is x2. It takes on one of 4 values, A, B, C, or D, that we're depicting by color. And then a continuous variable, x1, which we're depicting along the x-axis, and the response variable, y, along the y-axis. So we can fit 2 different models to this data because we have two different predictors. One is an additive model, and the other is a multiplicative model. So the first estimates each effect independently, and the second considers the interaction of the two along with the individual components. So this one has an interaction term plus an x1 term plus an x2 term. 2 functions can support visualizing these models. So we have the data grid function, which will generate all combinations of the unique values of x1 and x2, and gather predictions, which will generate predictions from both models simultaneously. So we can create this grid object from using both of these, using x1 and x2 in model 1 and model 2. And we end up with 40 different combinations of the 2 variables. And we have 2 models, so we have a total of 80 rows in this table, and with a prediction for each one. And we can visualize the results using faceting. So we're going to facet wrap on models. So we have 2 models, so there are going to be 2 facets to this. And we're going to have lines for the values that remember, the x2 coordinate takes on 4 possible values. So that means that we're going to have 4 geom lines in each of the 2 facets, plus the original data. So there's the result, and you notice that for the additive model, the slopes are all the same. For the multiplicative model, the slopes are all different. So this indicates interaction between the terms. But we don't know which model is better. We don't know whether the interaction is really significant or not. One way that we can find out is to plot residuals. So let's do that here. So we're going to gather residuals and we're going to plot the residuals along with SIM3. We're going to plot x1 along the x-axis and residuals along the y-axis, and with the color of x2. So this will be the residuals. This will be the scatter plot of the residuals, and then this facet grid being model times x2 is going. There'll be 2 times 4 of these, so there'll be 8 altogether. So, and you can see that there are 8 facets total. The top row refers to model 1, the bottom row refers to model 2. And so now the question of which model is better is easier to determine because we see this pattern, a very strong pattern in B, and we see a very strong pattern in D. So I would say that and there's no patterns here. These all look pretty random to me. And to the authors suggest that this model is better. It's captured more of the variability in the data. Okay, now we can do the same thing with 2 continuous variables. So we have this exact same situation of 2 plots. We're going to have more possible combinations. And the data grid is going to have this range, this sequence range. This is going to give us a series of values along the range of a vector, in this case 5 values. And we have 25 possible combinations of x1 and x2. So it's actually fewer combinations of x1 and x2 than what we had in the previous one. I think we had 40 combinations before. So we have 25 combinations here and 2 models. And we can visualize these models as 3D surfaces. And so we're going to use geom tile. So let me just show you this tile and I'll come back to this. So this is what we mean by geom tile. And the aesthetic that we're using is the magnitude of the prediction. So a larger prediction is going to be a lighter color and a smaller prediction is going to be a darker color. And we're facet wrapping this on model. So consequently, we're going to have 2 facets because we have 2 models. So this is the additive model here, and this is the multiplicative model here. And it's very hard to see a difference between these 2 models in this view. So what can we do about that? What we can do is plot a sideways view looking at slices of the model. So we're going to do geom line. We're going to do this twice. We're going to do it once with x1 along the x-axis and once with x2 along the x-axis. So this time we're going to have x1 along the x-axis and use x2 for color and grouping. And facet wrapping again on the model, so we'll have 2 facets. And the result appears to show interaction. But again, we don't know how good this model is. The interaction may be illusory. We want to plot the other sideways view. So here we put x2 in, and x1 is the color and x1 is the group. And we facet wrap, so we have 2 facets here. And again, it looks like there's interaction here. But we still don't know for sure which model is better. And in fact, the textbook authors mentioned that they tried to judge the models on the basis of the residuals and found it a close call. Now, since the data set is included in Model R, you can always check it out for yourself. We're not going to. I'm just going to move on. Also, if you took the KDD course, you probably know from me or from Chi, you know a few more techniques for evaluating residuals that you learned in that course. We're just going to move on to transformations, which we can use for a lot of things. We're just going to use them for 2 things here. We're going to straighten out curves and unbunch packed observations. So any transformation that involves any of these operators, plus, star, exponentiation, and minus, has to be wrapped in I parenthesis. And if you forget I parenthesis, weird things will happen. And you can always figure out what's going on by using model matrix. So here's an example. So remember we used model matrix before, so we need a model and we need a data frame. So here's the data frame. And so this is a messed up transformation. So here's our model. Our model is supposed to be x squared plus x. But what we see in the model matrix is exactly the same thing that we would see if we just had x. So that's not what we want. So that's a frustrating error. The first time that I tried doing a model in R, I didn't realize this, and so I couldn't understand what was going wrong. I looked it up and found out that I had to do this. So if I wrap this in I parentheses, then I get the interaction, I get the quadratic term. Now, another thing that I can do is, with quadratic terms, I can do a polynomial and a larger and larger polynomial to more and more precisely model a smooth function of any kind. And that's great, but the authors recommend against it, and I'm going to skip all the part where they recommend against it and just go right to what they recommended instead, which is to use natural splines. So we're going to load the splines library and try a natural spline of degree 2 on this data, and you see that we get we get more than what we appear to have bargained for, because we have this generates cubic splines of degree 2, degrees of freedom 2. So even though we appear to just have one term here, the model matrix is showing that we have 2 terms. And we can do this with many more terms, which we're going to do in a second. So here's an example of a nonlinear function that we might want to model. And this is just a cooked one. This is a sine wave function with some randomly generated, normally distributed error thrown in. And when we plot it, we'll see a sine curve. Okay, so we just have a sine curve. That's all this is. Sine curve with some normally distributed random error. Now we're going to try 5 different models with this and see that having higher degrees of this natural spline results in a closer and closer fit to the data. That's not always what you want, but in this case it's going to work out nicely. So we're going to do the same thing with this that we did before, creating the data grid. So we have this grid, and the geom line represents the grid prediction. And so we're going to have a colored red line, geom line, representing our prediction. And geom point is going to have the sim5 data set. And we're going to facet wrap this on model, and we have 5 models, 1, 2, 3, 4, 5 models. So we'll have 5 plots, 5 facets to the plot. And this is degree 1, degree 2, degree 3, and so on. And you can pretty easily see that degree 5 best approximates the function. Okay, so that about wraps it up. And as with other chapters, this slideshow just touches on the subject. You should really read the full chapter after viewing this. And the subsequent chapters on modeling will repay careful study, so check those out too. And as always, thank you for your attention.